Hello everyone and welcome. I'm Valérie Faudon. I'm the Director General for the French Nuclear Society, and I'm really happy to welcome you at the Index International Conference for Digital Transformation in the Nuclear Industry. This is our session number 14 for a total of 18 sessions. And so far, we had 1,000 attendees from 40 different countries. So this conference is a success. And I encourage you to look at the next session coming starting next week. So today we are very, very fortunate to welcome Dr. Sacit CETINER. So Dr. CETINER is a senior research scientist at Idaho National Laboratory, and he has also a joint appointment as the scientific director of the INL MIT Center for Reactor Instrumentation and Sensor Physics, CRISP. So we're really fortunate because Dr. CETINER is both an expert in artificial intelligence and an expert in the nuclear field. So he's really the ideal and fantastic speaker to talk to us about what is the status and perspectives for the use of artificial intelligence in the nuclear industry. So I'm going to give you the floor now for the keynote presentation. But before I give you the floor, I would like to remind everyone that we will have 15 minutes at the end of Dr. CETINER's presentation for questions. And to ask your questions, you can see on the top of your screen a little S, Slido. So you click on Slido and please ask your question. You can also vote for somebody else's question to make sure that this question will be asked in priority. So Dr. CETINER, I'll give you the floor. Thank you very much.
Thank you for a nice introduction, Valerie. I appreciate it. Today, I would like to talk about the use of artificial intelligence in nuclear industry with some example use cases that I gathered from my colleagues and from the ongoing programs within the Department of Energy and some executed in universities. We live in interesting times. Literally over the last decade, we've seen emergence of incredible advances and proliferation of digital technologies almost in all facets, aspects of our lives. We are now not surprised when we see cars driving by themselves or rockets returning back to Earth in a vertical position. And the success of these applications, they all relate to the expansion and acceleration of computational powers provided by digital technologies. On the left, of course, you see an obvious use cases, multiple use cases of artificial intelligence in the self-driving car technologies. While this technology has proliferated in the recent years, actually the initiation of the technology goes back many decades. For instance, in Europe, the European governments invested in highway efficiency and improved safety projects under a large program. And part of that program was, of course, improving the automation in automotive technologies. The very first application can be traced back to early 80s, where a van was driven on the European highways. Of course, that required a large compute resources. Today, these can be achieved in a small microcomputer box. The key technology, enabling technology in many of these use cases we see is artificial intelligence. And there are many algorithmic developments that enabled this expansion, but a key enabler is the ability to train those networks and be able to run these algorithms efficiently in automotive applications. So what I would like to talk about today is what are the analogous, similar use cases we can find in nuclear engineering applications, and what are the examples that we see today. So nuclear systems are complex organizations, and nuclear design constitutes a multidimensional, multi-scale, and multi-physics domains. When we design nuclear systems, we perform many design iterations to achieve an optimal configuration. Of course, with increased computational power, we can sharpen our pencils, we can improve our efficiencies, we can improve our safety posture. But to do that, even with the current computational capabilities, the complex phenomena involved in the operation of a nuclear reactor, these coupled multi-physics system, they involve large spatial and temporal scales. So here on the right, I give you an example of the computational fluid dynamics, where you start from lumped models, lumped parameter models, all the way to direct numerical simulations, where you resolve every turbulent scale available within the simulated domain. So we can achieve these mind-boggling, sometimes computational achievements, but even with today's computational powers and large federated clusters, computations from first principles are limited. And they are limited in spatial domain. For example, in DNS, we can perform it within a short section of a subdomain within millimeters to centimeters at most, and mostly for short periods of time. However, there are many phenomena involved that require coupled system level dynamic simulation. So for these applications, for these needs, a common use case for artificial intelligence methods, when I say artificial intelligence and machine learning methods, is the use of reduced order models. For example, here I give you an example from Raisi, where he used a physics-informed neural network model to solve the classical flow instability problem after a cylinder. Basically, what it does is creates a deep neural network and then trains the network on a large solution domain using Navier-Stokes equations. And then the learned dynamics, we see that the estimation error can be significantly reduced if sufficient training is performed. So of course, this is just one application, but I would like to give examples from a number of use cases in the nuclear application, in the nuclear industry. Some a little bit futuristic, and some actually are currently being used. This example comes from a colleague of mine from MIT, Professor Kåre Shirvan. So they were given a problem of fuel reload optimization, and it is an NP-hard problem, highly large combinatorial space. We're talking about 50 factorial, and it's about over 10 to the 64th possibility of fuel patterns. And just like to remind you that there are about 10 to the 79 to 82 atoms in the universe. So it shows the magnitude of the difficulty of this problem. And actually, we can also deduce how hard these problems are, because if it was easy, we could have found a solution already, and we haven't. And the problem is also exacerbated by other things, like having access to expert knowledge, or using expert knowledge in the entire life cycle of the optimization process. So what our colleagues did was to use reinforcement learning in a non-traditional manner. The reason they use reinforcement learning, which is a branch of machine learning applications, is because it allows incorporation of large number of constraints, and it allows use of undefined objective functions that define a balance with safety margin and operational risk and cost. But the contribution from the key contribution from the artificial intelligence is the ability to generate fast-running physics models. So here's an example that I pulled from their publication. Here on the right, you see a boiling water reactor fuel assembly design, where fuel rods are positioned in a way to generate an optimal configuration, fuel burn configuration. This was highlighted in MIT News about a year ago, and it goes like this. Typically, we see reinforcement learning applications and the use of evolutionary algorithms in the optimal construction of the hyperparameter space. Here, our colleagues look at the problem in a different fashion. They use it in an opposite manner. Instead of using evolutionary algorithms to optimize the reinforcement learning constructs, they instead use reinforcement learning method as a game rule guiding method to evolve to guide the evolution of evolutionary algorithms. And when I say evolutionary algorithms, there are plenty: genetic algorithms, simulated annealing, differential annealing, or swarm optimization, a number of evolutionary methods. What they demonstrated here is that the RL network, or the RL wrapper, acts like a Go player or an expert opinion enforcer, where the rules enforced into the reinforcement learning network drives the selection of proper genetic algorithm methods or evolutionary algorithm methods. What this means is, as we know, genetic algorithms or evolutionary algorithms are widely used as global optimization methods, but they are prone to getting stuck in local minima. What the reinforcement learning wrapper provides is to help the evolutionary algorithm move with the identifying candidate patterns and coming up with more optimal configuration solutions. Here, the performance in the reinforcement learning guided genetic algorithm was staggering, almost 1 to 10 improvement in identifying optimal candidate patterns in fuel loading. This particular project was funded by Exelon, which is one of the largest utilities in the United States. So I would like to move on to another application of artificial intelligence. So first, I talked about use of neural network methods, particularly physics-informed neural network, is gaining attention. In reduced order models, then I mentioned using reinforcement learning kinds of methods for optimization purposes. But there are other applications that we can find and actually probably easier to adopt in the industry. Here, I would like to take your attention to the light water reactor sustainability funded series of activities. This particular one is on developing a predictive maintenance strategy, a plant-wide predictive maintenance strategy. But before I get into that, just briefly, light water reactor sustainability is one of the Department of Energy, Office of Nuclear Energy funded programs whose mission is to extend the life of the current fleet and improve the efficiency and efficacy of these generating technologies. So in the predictive maintenance approach, the idea is to move from a reactive maintenance strategy to more proactive. What this means is similar to what pretty much our bodies through our evolutionary success developed. For instance, we sense pain. We understand things going wrong before they break. And we are able to do that because our brain is able to fuse sensors, many millions of sensing points from our entire body to generate that local and sometimes global information. We don't know the exact value of something going wrong, but we can tell that qualitatively in our body something is wrong. And we can take the similar analogy to large-scale complex systems such as a nuclear power plant. So here, predictive models and the advancing and bringing the abilities of predictive modeling into risk modeling, and then create a risk-informed predictive maintenance strategy for improved plant operations. What this means is by monitoring multiple assets and sensor readings from multiple assets, we develop an understanding about the condition of the plant, and then based on the diagnoses, based on the prognoses, such as remaining useful lifetime, by identifying these fault precursors, we are able to identify and schedule our maintenance activities in a more efficient manner, and which is a great, a critical economic benefit for nuclear industry. This particular project is being executed by my colleague, Dr. Vivek Agarwal from Idaho National Laboratory. Here, as I mentioned, you monitor assets from multiple units, from multiple components, of course, the rotating equipment and particular active components, particular rotating equipment such as pumps, circulators, fans. These are, of course, things that are more prone to failure when it comes from a maintenance standpoint. But the aggregate system model, the aggregate machine learning model, it's a combination of individual models leading to a master model. But within this machine learning model, we are able to feed in sensors from different modalities that can provide good indications of the condition of an equipment. Obvious ones are vibration, temperature for electrical equipment, of course, electrical signature analyses. These all can provide very useful information, and when combined, actually they provide, through cross-calibration, cross-correlation, they actually provide information and confidence in their prediction capabilities. Here, I would like to give a little bit smaller example from a project that I was involved. Here, we used sensor fusion application in an experimental test loop. This is a small test loop operated by one of our colleagues, a private company, and the key thing about this test loop is that it is highly instrumented and provides a great range of vast area of redundancy for creating of virtual sensors, and particularly in the sensor fusion application, gives a very rich set of data that can be used for regression purposes. What the application, this particular application, looked into was to first train a set of machine learning models. And I use the term machine learning models in a broader sense. For example, in this particular case, I'm giving two examples from two model constructs. One is ensemble of trees. The other one is support vector machines, both successful machine learning algorithms approaches. And the idea is, in the event of a drift in one sensor, can we predict the true value of the quantity of interest? And what we show is, if trained properly, both machine learning applications perform impressively well in predicting the true value, and actually also identifying the false reading in a particular sensor. However, the problem is, what is the confidence in our measurements? What is the error, expected error that we get from these data-driven models? Here's a dilemma. The machine learning models, if trained properly, they perform impressively within the trained domain. But if you move out into a set outside of the trained domain, then the prediction performance can deteriorate significantly. So that is something that needs to be quantified for any application, particularly in applications where regulatory approval is necessary and public safety is of concern. In this case, again, funded by the Light Water Reactor Sustainability Program, we looked at the generalization error bounds. Let me tell you about generalization. Generalization is a term used in statistical learning models. It's usually considered one of the most important attributes in evaluating a learned model. Generalization performance of a learning model, it relates to its ability to predict on a set of unseen samples from the distribution same as that of the training set. Assessment of this performance is very important, and this is the unique contribution of this particular publication, where the sensor fusion applications, including support vector machines and others, were demonstrated before successfully. But what we here demonstrate is using the generalization equations based on, in this particular case, Vapnik-Chervonenkis measure. We show that we can actually bound the prediction prediction performance of these complex data-driven machine learning structures. And we demonstrated that the mean square error of a support vector machine is about 87% with about 95% confidence. This is pretty good, but still not good enough. The EOT showed better performance, but of course, as you can see, the math, the derivation process to come to this point is mathematically involved. Just want to point out that these derivations were done by one of my summer interns over a period about 2 months. So this is an area that needs to take attention for our industry. Okay, let's get back to anomaly detection. We talked about predictive maintenance. We talked about moving from reactive maintenance strategy where something fails or at the minimum an abnormal indication is received and then a maintenance activity is started. However, a more sane approach would be a comprehensive aging management strategy, where predictive maintenance is a key part of the operational strategy and part of the maintenance plan going forward that is submitted to the regulator. Here, we use our colleagues, in this case, my colleague, Dr. Ahmed Al-Rashdan, shows how damage precursors can be used or fault precursors can be detected to identify anomalies in the operations. The example here is a dry well fan coil in a BWR unit. In this example, the dry wells, 2 dry wells failed and leading to plant outage for 6 days. So every day, considering many multi-million-dollar revenue losses, this is very very critical. So in this particular application, they used different machine learning applications, unsupervised or supervised, semi-supervised machine learning applications. I don't have time to get into the details, but the bottom line is to detect anomalies before they manifest. Of course, in this particular case, the anomalies had already manifested, but looking at the time series historical data, they were able to demonstrate that the prediction was possible about 10 days prior to the failure of the fence. So if they had acted prior to the gross failure of these fans, they probably could have avoided a protracted shutdown period of 6 days. So moving forward, another interesting application again that comes from the light water reactor sustainability is the operator rounds. As you know, operators, field operators, they go around in the balance of plant systems and look for gauges, read gauges, or look for equipment condition. Here they developed a very simple yet elegant strategy where the robot looks for QR codes strategically located in close proximity to equipment. So the drone goes from one room to another or one location to another in the close spaces of the balance of plant and looks for critical information needed. In a different application where a wide angle camera and a small and a narrow angle camera were used to read gauges automatically and generate digital information directly from the calibrated analog sensors. These can look simple, but these applications save a lot of time and a lot of effort. Another use case that is being piloted in some of the utilities is the use of AI to detect power plant firewatch activities. Here, the neural network, a convolutional neural network, is able to identify existence of flames within a very short amount of time and with very high, over 99.5% prediction accuracy. Here's this is a recent application of artificial intelligence, but in this case, not in the operations domain, but in the business optimization domain for performance tracking. This particular application called Machine Intelligence for Review and Analysis of Condition Logs and Entries, Miracle. This particular one looks into maintenance reports, millions of maintenance reports, and builds a large dictionary and graph network, and using the natural language processing power of the artificial intelligence methods, they are able to identify the SATA significance, whether issue is repetitive, and identify actually a priority, assign a priority for it, and identify its severity level. This particular application by our colleague Ahmed Al-Rashdan won the 2022 R&D 100 award, which is a big deal in the US. So again, I would like to take our attention to a non-nuclear application to draw an analogy. In this case, for autonomy. Autonomous control is, of course, with the emergence of self-driving cars in our daily lives, autonomous control, particularly for smaller reactors and especially for microreactors and nuclear batteries, became a critically important capability. But in this case, what I would like to take your attention is where the autonomy requirement comes from. It comes from the mission, because the round-trip communication time in these systems is prohibitive for human intervention. By the time the entire descent process is about 2 minutes, and the round-trip time can be 25 minutes, depending on where the planet is located. And by the time you take an action, it's already over. The mission is finished. So what we observe here is that the NASA crew, when they announced this particular submodule of the rover landing unit, the terrain relative navigation system and the landing vision system that's part of it, when the engineers announced that it converged to an acceptable solution, you hear the loud applaud coming from the engineers. So here my question is, where is AI in this? In 2020, the U.S. government, the White House, issued an executive order instructing federal agencies to disclose their use cases for artificial intelligence. And by looking at the recently released records from NASA, we see that even on the Mars 22 rover, which was a very successful mission, we see an abundant use of artificial intelligence, neural network, and machine learning applications, and many different ones, from visual tracking purposes to obstacle avoidance. So here's the critical question is, we want autonomous system, but what is our problem statement? What is our mission driver? So for those who are in the area of instrumentation and controls, they know that the traditional feedback control systems, they are capable of maintaining key variables of interest like temperatures, flow rates around design, or power around desired set points. This is mature, but the use of decision-making capabilities and potentially with some artificial intelligence and neural machine learning implementations to assist with the decision-making capabilities, these approaches begin to make sense when the plants start to undergo major operational swings. What are those? These are mode transitions, going from cold shutdown to hot standby to low power and gradually increasing power. Especially with smaller reactors and with the even more recent discussion on microreactors deployed in non-traditional energy generation scenarios, such as being used in local grids or used in disaster relief efforts. These systems will have to go through frequent maneuvers because now they're not connected to an infinite grid. So we expect a higher frequency of failures just by virtue of faster equipment wear due to higher duty cycles. And what I envision is that because of these complex combinatorial effects that will create large uncertainties, we will have to come up with sequential decision-making methods that can perform operational decisions, just like an operator, to enable autonomous and semi-autonomous capabilities. And with that, I would like to finish my presentation. And Valérie?
Thank you very much, Sacit. So thank you very much for all these use cases. It's really interesting. So we have a few questions. Please ask your questions by clicking on Slido, and you can vote on some of the questions that have already been asked by Jean-Bernard in the system. I wanted to ask you, we have lots of questions on safety applications and discussion on safety applications of artificial intelligence. And I understand there's been a report in the United States published by the Research Bureau of the NRC with 5 strategical recommendations. So what is your opinion on the use of artificial intelligence and safety applications, and what is the conclusion from this report?
So Valérie, I'm aware of that report, but that report does not constitute any policy changes by the Commission. In fact, in a recent ACRS panel review, ACRS stands for Advisory Committee on Reactor Safeguards, the ACRS members questioned the NRC staff on the need to issue that document. Issuance of that document, if you look at it carefully, does not say anything about the adoption of artificial intelligence in safety applications. What it does say is that the staff, the Nuclear Regulatory Commission staff, would like to be informed about and be prepared for potential applications coming to the Commission for review of cases where artificial intelligence or neural network applications, machine learning methods were used. So it is in preparation for a future wave of applicants. But what I would like to say is the NRC actually has been involved in and proactive in tracking the state of the technology by being by sponsoring a number of workshops and conferences in this field, particularly in the area of digital twin and use of digital twin in nuclear systems. I would like to point out that safety may not be the immediate use cases of artificial intelligence methods, and actually may not be the most cost-effective or cost-reducing approach for improving the life cycle lifetime cost value of these systems, but applications in the operations domain, they don't require as rigorous reviews, and they actually prove to be more potentially to more cost-saving measures.
More cost-saving measures. That's what, like in your use case you showed. I have a question on, because we're seeing now a lot of concepts that are like reactors, that like micro reactors that are supposed to be remotely operated. So, and we also see lots of reactors that are operated in a load follow mode, or at least more and more reactors that will be operated in load follow. So do you see any application for AI for this remote operating, or for this load follow, that means in the operations of these new concepts?
Well, not directly, but indirectly. What I see is load following. Your country has been doing it successfully for many decades. So it is not the controlling of a nuclear reactor is actually a boring problem for a control systems engineer. It is a stable system as long as it operates within bounds. But the remote operation is a new paradigm where you have minimal to no staffing on site, maybe one operator operating more than one unit, but then the majority of the operating crew works out of a common location, operating center. It brings in a lot of course, cybersecurity related questions, but what I see in these cases is we preserve the safety system architecture, and really safety systems, they are simple, and despite their simplicity, qualifying those safety systems and particularly the software qualification process is incredibly expensive. I just cannot think of going into any length of qualifying a complex black box model like an artificial intelligence within this regulatory environment. But use of AI again in identifying early identification of equipment degradation before they fail, and then taking proactive actions. Actually, these are potentially can lead to more cost-saving measures.
So I have in Slido, I have some rather technical questions. So I hope I can read the question because this is a field where I'm not that knowledgeable. So, do you think one day AI could be used as state reconstructor or observer for non-measurable state variables such as fouling, clogging, etc.?
Yes, definitely. And actually, the sensor fusion example that I showed it uses a simulated blockage in a differential pressure sensing line, which is akin to, for example, a blockage or partial blockage in a channel. So if we train a model of a standard system or a functional system, and then we observe some divergence or some departure from nominal performance indicators, not nominal quantities, for example, move from a departure from the standard pressure drop, those can all be an indication of potential blockages, such as caused by fouling. We've actually done these kinds of statistical analyses in the 70s and 80s, and methods like statistical probability ratio tests, they are also very successful. But what the artificial intelligence methods bring is they combine sensor readings, data sets from multiple sensors, and create an ensemble of indicators, bringing all the cross correlations into one physical representation. And that is very powerful. And yes, definitely, those I think the use of AI in that particular use case is absolutely possible.
Okay. Okay, so we are finished, but I will take one question again, and that is the last one. So do you think evolutionary algorithms are not enough well known and used for optimization problem in nuclear?
I wouldn't say that. The example I gave is an NP-hard problem. It is, first of all, it is a non-continuous problem, and it involves many combinatorial evaluations that lead to an incredibly large state space. So evolutionary algorithms are successful, but yet they may again fall into this local minimum traps. They are not, or they would require many evolutionary epochs to be able to generate optimal candidate solutions. What reinforcement learning algorithm here does is brings in an expert opinion in an automated fashion.
Thank you very much again, and thank you for your questions and for your attention to all the participants. And thank you very much, Dr. CETINER. Talk to you soon. Thank you very
much for the invitation. Have a nice day.
Bye-bye. Thank you.